All right. Thank you, Jalal, and the organizers for the invitation and to speak here. So today I'll be talking about a recent work in collaboration with Yu Deng on the full derivation of the wave kinetic equation. So as Jalal mentioned, we will be going more into some of the details of this work in a couple of other talks towards the end of the month with Yu Deng. I was asked to give a somewhat of a colloquium style or a seminar, normal seminar talk on this result today. Okay, so let's get started. Everything that we'll be talking about falls under the umbrella of Hilbert's sixth problem, which asks for axiomatic derivations of the laws of physics from first principles. And the main example over there is to justify the laws of statistical physics starting from the laws of dynamics. So in other words, you take the laws of dynamics as axioms, and you want to derive out of those axioms in a mathematically rigorous arguments, the laws of statistical physics. So the statistical laws govern macroscopic quantities, as we all know, things like temperature, pressure, fluid velocity, and those are typically time irreversible. Think of the second law of thermodynamics. On the other hand, the dynamical laws govern microscopic quantities, things like trajectories and orbits of dynamical systems, and those are typically reversible in time. Here we think of Newton's laws and Hamilton's equations. So the problem or the main difficulty is this passage from the reversible to the irreversible, which comes as a result of a sequence of averaging and limiting operations. And this sequence is what creates the arrow of time, this preferred arrow of time that appears in the statistical laws, but doesn't appear in the dynamical laws. So this will be the main problematic for now. There's a classical example of this problematic, which is Boltzmann's kinetic theory. So it was Hilbert's suggestion that this passage from the microscopic to the macroscopic should happen via an intermediate mesoscopic scale, which is given by the kinetic theory. Main example here is Boltzmann's kinetic theory. So over there, the class or the microscopic system is the system of n Newtonian particles, each having radius r, and those particles are undergoing elastic collisions. And in that case, one can derive an effective equation for the one particle density functional. So this one particle density functional, you can think of it as the probability of finding a particle at position x moving at velocity v. And Boltzmann's theory tells you that the effective dynamics of this one particle density function is given by the celebrated Boltzmann equation, which I write partially here. This Q of FF is a bilinear collision kernel. And the justification of this approximation was a big challenge, and it was finally done by Lanford. And there's a lot of works that needed to sort of fill in the details of Lanford's proof and extend it. So I'm most familiar with the work of Gallagher, Saint-Remo, and Texier, which might be the most sort of gives the most extension and fullest proof as far as I'm familiar with. So what does Lanford's theorem say? Lanford's theorem tells you that Boltzmann equation appears an effective equation for this one particle density functionals in the limit when the number of particles n goes to infinity and the radius of each particle goes to 0. And this is justified not in general, but only in this, what is called the Boltzmann grad scaling law, where n goes to infinity and r goes to 0 according to this law, such that n times r to the d minus 1 is comparable to 1. Okay, so the approximation says that this one particle density functional can be approximated in the limit n goes to infinity, r goes to 0 by this solution of the Boltzmann equation up to times that are basically 1 over rho inverse. This rho is called the collision rate. And this kinetic framework has been highly informative in many applications and was extended to understand the long-time behavior or the effective statistical mechanics of many other particle systems. So what we'll be interested today is to look at and understand the wave analog of this problem. So 20th century physicists drew a parallel theory of statistical mechanics for nonlinear wave systems. In this setting, the microscopic dynamics is given by a nonlinear dispersive PEE, as opposed to like Newton's equations. So instead of the large number of particles, we have a large number of waves, which will be represented by the Fourier modes of the solution. And this solution will be in a box of size L, with L being the asymptotically large parameter. And these waves undergo sort of what stands for collisions, and these collisions are the nonlinear frequency interactions that are given by the dispersive system. So today, and to make things concrete, I will only be talking about the nonlinear Schrodinger equation. So this is, we're all familiar with this model, the cubic nonlinear Schrodinger equation. So this will be posed on a box of size L with periodic boundary conditions. So this box of size L could be rational or irrational. It has aspect ratios gamma 1, gamma 2, up to gamma sub d. And we say that this torus, or this box with periodic boundary conditions, is irrational if gamma 1 up to gamma d are rationally independent. This means that k dot gamma is different from 0 if k is not 0. And we often sometimes impose generic irrationality on the gammas, not just irrationality. So in such a way that they also satisfy a Diophantine condition. And one can think of course, one can think of such solutions as periodic solutions on RD with period that is similar to L, where L is diverging to infinity. So the solutions of interest for the kinetic theory are ones, as we will see, those are ones that have total energy being diverging with L. As L goes to infinity, the total energy will diverge of the system, but the local energy will remain finite. And this is typically what happens in thermodynamic limit. This is also something that happens, for example, in the Boltzmann limit. So as with any theory of statistical physics, we'll be talking about it in a couple of slides. The aim is to understand the long-time behavior of the solutions. And the understanding of this long-time behavior deterministically is practically impossible. And this is due to the rich set of long-time dynamics that can be exhibited by the system, including the NLS. So you can see periodic behaviors, you can see quasi-periodic behaviors, soliton-like, and other potential type of behaviors. But even on RD and for finite energy solutions, where asymptotic behavior might be understood. For example, if you consider a defocusing equation, and sometimes we have results like scattering for finite energy solutions. While this asymptotic behavior is quite well understood, the intermediate time behavior of large solutions is not well understood. So as such, just like for particle systems, a statistical approach is needed to understand the behavior of generic solutions. Okay. So let's see how this theory goes about doing that. So there are two parameters of the problem. We've already encountered one of them, which is the size of the domain L, or the size of your system, which is related to the number of basically frequencies that are available to interact. So the other parameter is the characteristic size of the solution. So here, in order to emphasize this size of the solution, we'll adopt the ansatz V equals lambda U, and think of U as having size order of 1 in L2. The L2 norm is conserved for this equation. So the equation satisfied by U would be essentially the same as that satisfied by V, but you have a lambda squared in the nonlinearity. So here I also rescaled space so that we'll be working on a square torus of size L. So now this is just the square torus of size L, but this comes at the expense of twisting the Laplacian a little bit. So you have those beta 1 d by dx1 squared up to beta sub d d by dx d squared, and these are of course related to the aspect ratios of or define precisely the aspect ratios of the torus. So it turns out that it is more convenient to state the result in terms of, not in terms of the parameters lambda and L, but in terms of a parameter alpha and L, where alpha is lambda squared L to the minus D. So this alpha is we call it the characteristic strength of the nonlinearity. Okay, so we define alpha as such, and we'll state our results using alpha rather than lambda because they look a bit nicer there. And heuristically, why am I saying that this is the characteristic size of the nonlinearity? Heuristically, we'll be dealing with generic solutions in L2. So say we're talking about this U solution. Its L2 norm is order of 1. Then it's, if we pick a generic field over there, this will have L infinity norm with high probability that is order of alpha minus t over 2. So if we look at the size of the nonlinearity, this is something that has size lambda squared L to the minus t. You put one copy of U in L2, 2 copies in L infinity, and you'll get this alpha. Of course, this is a heuristic argument, but it turns out to be the case. This alpha is for the solutions that are considered in the kinetic theory, and in our proof, this is indeed the strength of the nonlinearity. Okay, so finally, we'll get to the randomness that is inherent in the theory. So the way we'll introduce randomness is by taking random initial data. So, and this is the same that happens, for example, in Landfor's proof and in the many particle case. So we start with the random distribution of initial data. This corresponds to taking random and independent Fourier modes for the initial data for our NLS equation. So we'll take U initial to be expanded in Fourier modes as such. This is the usual Fourier mode expansion, but we'll take the Fourier transform of U initial at K to be given by the square root of N initial at K. So this N initial is just a nice Schwartz function on RD. But the key point is that we randomize them, or if you like, we randomize their phases according to a IID family of random variables, which is eta sub, which we call eta sub K. So here, K ranges over a lattice of mesh size L inverse, which is the Pontryagin dual of the torus of size L. And initial, as we said, is a Schwartz function on RD, and those eta K are IID normalized Gaussian random variables. Okay, we call this this kind of initial data to be well prepared, because eventually we will see that we would want to prove a effective dynamics for the expected value of the Fourier mode squared, and we want to compare those to the evolution of the wave kinetic equation, which will be the analog of Boltzmann equation. So we want this approximation to hold at time 0. So for it to hold at time 0, we need this to be true. So that's, and this choice of initial data is exactly what guarantees that. Okay, is there a question? Okay. All right. So as I was just saying, the goal of the wave kinetic theory is to understand the distribution of the Fourier modes at later times. So we are starting with a distribution for which the expected value of the modulus of the Fourier modes is given by some initial distribution and initial of K, and we would like to see how this evolves, the expected, how this expectation evolves. And this kinetic dynamics appears in the limit when L goes to infinity and alpha goes to 0. And this limit replaces the limits N goes to infinity and R goes to 0 in the Boltzmann's particle theory. Okay, so what does the main conjecture of wave turbulence theory, what does it say? It says that in the limit as L goes to infinity, so this is the large box limit, and alpha goes to 0. This is the, as we said, alpha is the strength of the nonlinearity. So this is the weak nonlinearity limit. It tells us that the effective dynamics of the this mass density is given by the wave kinetic equation, which will be a kinetic equation that I will write on the next slide, and rescaled up to the kinetic time, which is 1 over alpha squared. So in other words, you expect to see the dynamics of the wave kinetic equation at this kinetic time scale. More precisely, what we expect is the following. This is what I will call approximation later in the talk. We expect that the expected value of the mass density to be, which is a solution, this is the solution of the NLS equation with initial data U initial, is approximated by the solution of the wave kinetic equation at the time scale T kinetic, so at time T over T kinetic, plus an error that goes to 0 as L goes to infinity and alpha goes to 0. So as we said, N is the solution of the wave kinetic equation with initial data and initial, and U of t is the solution of the NLS with initial data U initial. So this notion of well-prepared initial data is just to guarantee that this approximation holds at time t equals to 0. Okay, so I owe you a statement of what this wave kinetic equation looks like. So it's familiar to many of you. So this was formally derived in the physics literature and has the form dtn is equal to a trilinear nonlinearity, k of n and n. Its initial data is n initial. And this trilinear nonlinearity is written over here. So you're integrating over the set xc1 minus xc2 plus xc3 equals to xc. So here xc is an RD. And there's a delta function for the resonance factor, xc1 squared minus xc2 squared plus xc3 squared minus xc squared. So this has to be 0. And then we have this integrand, which is n at xc1, n at xc2, n at xc3, n at xc multiplied by this. Okay, so this is a wave analog of Boltzmann's equation. And we notice that this kinetic approximation also features a passage from the reversible analysis equation into the time irreversible wave kinetic equation. I should point out here that one could also study inhomogeneous versions of this equation in which you would have a term like c dot grad n over here, grad x and n. So n would be dependent on the space x and on the frequency variable xc. And then the wave kinetic equation looks exactly the same, except that with the transport term over here. Okay, so we won't be discussing that inhomogeneous version of the equation today. All right, so let's talk about some of the physics literature related to this. So the emergence of the wave turbulence theory was roughly in the 1920s. Sorry. In the 1920s, and I believe the first paper that I know of is that of Peirce around 1928. Since then, this kinetic formalism was generalized tremendously to many nonlinear wave systems. For example, in the context of water waves, the kinetic equation is called the Hasselmann equation, and it was also written in the 60s. In the case of anharmonic crystals, this is sometimes referred to as the Phonon-Boltzmann equation. And there are also many wave kinetic equations in plasma theory. So, and as for Boltzmann, as for any kinetic theory, this is highly informative in applications. And most notably, it leads to a formal framework of turbulence for nonlinear waves. And this is why this theory is called wave turbulence theory. So formally, at least, it gives conclusions similar to those made in hydrodynamic turbulence, particularly relating to power law cascade spectra. So these spectra come out as stationary solutions of the wave kinetic equation, and these are sometimes called the Kolmogorov-Zakharov cascade spectra, which were discovered by Zakharov in the 60s. Okay, so here I refer to Nazarenko's excellent textbook on this, and there are also some works to make on the rigorous side by Escobar, Velasquez, Sofer, Tran, and others. Okay, so this is a good segue to start talking about the mathematical literature. So influenced by this field of physics, the initial focus of the mathematical research was related to wave turbulence was on constructing solutions that exhibit growth of Sobolev norms, solutions of the nonlinear Schrodinger equation, for example, that exhibit growth of Sobolev norms. So such growth is actually predicted by those cascade spectra over here. And one way to exhibit it in a rigorous way is to construct solutions that exhibit the growth of Sobolev norms. So this line of research was started by Bourgain and Stafilani, who first derived upper bounds on the growth. Then there was this probably the most influential paper on this direction is the paper of Polander, Kiel, Stafilani, Tekok, and Tau, who constructed finite but large growth of Sobolev norms. And then there were several contributions by many people, including those listed here. Okay, but the central question remains is to give whether we can give a rigorous justification of this kinetic approximation that we mentioned in the equation we called approx. So mathematically, this would provide a precious insight into long-time behavior of the solutions of NLS, including questions related to energy cascade and growth of Sobolev norms. And from a physical point of view, this is also would be valuable because this is important to understand the exact regimes and limitations of wave turbulence theory. So in terms of works in this direction, there were several works that attempted either this problem or similar questions. So there's the first one probably that I know about is the work of Lucanen and Spohn, who studied a similar problem, basically understanding time correlations for Gibbs measures. So here, the initial distribution, and which is invariant, is given by Gibbs measure. Another way to introduce randomness, by the way, to the system is to introduce, to force your equation, to have a time-dependent stochastic forcing to the equation, which sort of might help you in pushing your system towards the needed ergodicity or Gaussianity that is needed. So there are several works here. There's a work of Fau, who considered a KdV equation with the Stratonovich type forcing and was able to derive a linearized version of a wave kinetic equation there. There's the work of Dymov and Kuxin, and later Dymov, Kuxin, Mioki, and Vladots, who study the equation that is forced by white noise. And there's a new work, which I believe should be coming out very soon, of Stafilani and Tran on a high dimension KdV type equation with, again, Stratonovich forcing. I believe it's the same model that Fau studied. And there it's a very nice and deep work. So they derive the corresponding wave kinetic equation at the kinetic time. And they also have a conditional result in the deterministic setting when you have zero forcing. And they verify that this condition is satisfied for some distributions that converge to the equilibrium distribution in the limit. Okay. But in the deterministic setting, if we leave the equation deterministic, the first attempt at the full problem was in the work of Buckmaster, Germain, myself, and Jalal. And in there, we initiated this study of the rigorous derivation for NLS. And we were in the setting of generic irrational tori in dimensions d greater or equal to 3. And there we justified this approximation, but for short times. The drawback was that the time of approximation of our theorem was much bigger than 1. It was a long time, but it was still considerably shorter than the kinetic timescale. Okay. In later works of myself with Yu Deng and independently by Collot and Germain, we improved this approximation interval considerably, all the way up to t less than L to the minus epsilon times the kinetic timescale. So it's sort of, we'll see that this corresponds to a subcritical range of the problem. So, and this epsilon could be made arbitrarily small. Okay, but this we only even, I should point out here that we're only able to do that for some particular scaling laws, which brings us to the next point, which is the notion of scaling laws, which turns out to be an important notion in this line of work. All right, so what is the scaling law? We've already encountered one example of a scaling law in the Boltzmann-Brad limit when we were discussing Boltzmann's theory. So the scaling law essentially dictates how is the limit L to infinity and alpha to 0 is taken. What are the relative rates of those things approaching their limits? So a priori, you might say, okay, I want to consider all possible choices of this scaling law. So we consider various scaling law of the form alpha equals L to the minus gamma, where gamma is between 0 and infinity. The case gamma equals 0 would correspond to taking the L to infinity limit first and then followed by the alpha to 0 limit, and vice versa for the case gamma equals infinity. Well, it turns out that it's not, you won't spend too much time before noticing that not all scaling laws are admissible by the kinetic theory. If you want your system to converge actually to the kinetic equation, not all of those, not all this range is admissible. And this, the admissibility range can depend on the shape of your domain. Okay, for example, in our case, on the aspect ratios of the torus. For example, if you don't impose any condition on the torus for general tori without any genericity assumptions, even without the assumption that the torus is irrational, you are stuck with this regime that gamma has to be between 0 and 1. This is the only admissible regime. For generic tori, in the generic irrational case, this regime sort of widens a little bit into 0 between gamma between 0 and b over 2. Okay, so these are at least, for example, in this regime, these are come from out of some number theoretic approximations that were actually dealt with in our work with Buckmaster, Germain, and Jalal. Okay, and it seems that the interest in one scaling law over another might depend on the physical context. We'll talk about a little bit more about this in a couple of slides. Okay, so going back to those works of myself with Yudeng and the independent work of Collin and Germain. So there we proved the approximation up to times that are almost approaching the kinetic time scale. So it's L to the minus epsilon times the kinetic time scale. In the case for two scaling laws, when gamma is equal to 1, so alpha goes to 0 like L to the minus 1, or gamma equals epsilon, so alpha goes to 0 like L to the minus epsilon. So these we call those two favorable scaling laws for which we were able to get to this time. And we also had partial results for other scaling laws. I don't want to go into the discussion of these partial results and why they are partial today. But I want to mention that the work of Collin-Germain also gave the same result in the scaling law gamma equals to 1. There was a later work of Collin-Germain in 2020 that studied the case of rectangular tori, generic rectangular tori that might not be, sorry, generic non-rectangular tori that might not be even rectangular. And in that case, they were able to get up to this time in terms of the existence of the solutions, not quite in terms of the approximation with the kinetic equation. All right, but all of those works still fail to reach the kinetic timescale T kinetic, and one could a full justification of the equation should reach times that are sort of order of 1 multiples of the kinetic timescale. So in other words, one should reach times that are delta times the kinetic timescale, where delta is greater than 0 and independent of L and alpha. Okay, so this is precisely what we did recently again with Yudeng. So here's the theorem. It states that we consider an LS on the torus TD with dimension D greater or equal to 3 and generic beta. I'll talk a little bit about this genericity assumption and when can we remove it in a minute. So assume we take the initial data for the wave kinetic equation to be a Schwartz function. Again, this is an overkill. We only need finitely many Schwartz norms to be bounded initially. And we take the initial data for the wave for the nonlinear Schrodinger equation to be well prepared, as we discussed. We adopt the scaling law alpha equals L inverse. And in this case, the kinetic time scale, which is always 1 over alpha squared, would be the kinetic time scale would be L squared in this case. Then we what is proved is that there exists a delta less than 1 that depends on an initial and an absolute constant nu greater than 0, such that the approximation holds as we like. We have that the mass density or the expected value of the mass density is approximated by the solution of the wave kinetic equation at time t over t kinetic with an error term that is polynomial in L to the minus nu. So this goes to 0 as L goes to infinity. And this approximation holds, the key point is that it holds for all times between 0 up to delta times the kinetic time scale. Okay, so at the end of this time scale, you're evaluating or you're looking at the solution of the wave kinetic equation at time delta. All right, maybe I could make this, well, I'll get to this remark in a minute about the genericity assumption on beta. So let's do some remarks on this result. This is the first result for of this type for a nonlinear dispersive equation. And well, we stated this result for one scaling law, alpha equals L inverse for definiteness. The same proof actually extends to scaling laws of the form L to the minus gamma for gamma that are sufficiently close to 1. And for the key point is that for such scaling laws, there's no genericity assumption on the shape of the domain that is needed. Okay, so the minute your scaling law falls below gamma equals 1, there's no need for the genericity assumption on the torus. The result holds for any torus. Okay, and we plan to do a systematic study of the other scaling laws between 0 and 1 in a future work. But at least when gamma is close enough to 1 and smaller than 1, the same proof goes through. All right, so why the scaling law alpha equals L inverse? This carries a particular mathematical importance because of the way the result scales back to the unit torus. So as we said, the kinetic time scale is always alpha to the minus 2, right? So in this case, when alpha equals L inverse, this kinetic time scale is L squared. So you're talking about solutions on a box of size L up to times that are L squared. So this is rescales back to the unit torus and gives you results at time 1 because of the parabolic rescaling that the NLS enjoys. Okay, so in particular, we obtained the dynamics of Littlewood-Paley projections of the Gibbs measure in 3D. For example, in the 3D case, if you rescale it back, you obtain the dynamics of, or the effective dynamics of the Littlewood-Paley projection of the Gibbs measure in 3D. And this is what links our theorem to the still open, very important open problem of the invariance of Gibbs measure for the 3D cubic NLS, which, by the way, is the only remaining unsolved Gibbs measure problem for NLS up to now, after this sort of impressive recent works of Deng, Nahmod, and Yuan. Okay, so here this would be a good segue to start discussing the difficulties of the problem. A common thing between those two problems, basically I'm referring to the problem of the invariance of Gibbs measure in 3D, and our problem is that both of them are probabilistically critical problems, as we will explain below. And this is one of the major difficulties to overcome for both problems. Okay, so I'm sorry if I'm going too fast, but please feel free to stop me whenever you feel the need. So let me, for the rest of this talk, I will try to give a high-level overview of the proof. So our proof is based on the idea of expanding the solution of NLS into what is called its iterates. These are the Picard iterates, and arranging those iterates in terms of Feynman diagrams. So we will be writing the solution as U equals U0. So this is the 0th Picard iterate, which is e to the IT Laplacian, the initial data. This is the first iterate up to U sub n. And so this U sub n is a multilinear Gaussian expression. So each of those U sub n only depends, they are expressions in terms of the initial data. They are the iterates. And the initial data was given as we said before, as a basically when we talked about well-prepared initial data, each Fourier mode was multiplied by a Gaussian in a way. Okay, so let us talk a little bit about how to represent these iterates by trees or Feynman diagrams. So let's start with the 0th iterate. So the 0th iterate is, as we said, e to the IT Laplacian. Give myself some space times U initial. So in Fourier space, this looks like the effective quantity of interest is the Fourier transform of the initial data at K, and this will be represented by a very simple, a trivial tree with one vertex and decorated by this K next to it. Okay, so the first iterate would be I of U0, 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 where I is the Duhamel integral. Okay, and in Fourier space, this can be represented as sum over K1 minus K2 plus K3 equals to K. U initial hat at K1, U initial hat at K2, bar U initial hat at K3. And whether you do what is called the interaction representation or not, there's a factor of e to the I omega t. So this will represent it as a tree which is decorated as follows. The root of the tree is K, and we put at the leaves, it has 3 leaves, K, we decorate them as K1, K2, and K3. Okay, so this expression would translate exactly to this expression in Fourier space. Let me try to do one example of U2. So in U2, you take the Duhamel integral, you put in U1, for example, U0, U0. You could have put in U1 here instead, and then you get another iterate. So in this case, I'll not try. I won't try to write down the Fourier mode, but let me show you what the tree would look like. So you started with this. You start with this tree over here, and then you branch out of the first leaf because you're replacing the first copy over here by U1, and you do it as such. Okay, and then if this was K1, K2, K3. Okay, and then over here you would have maybe N1, N2, and N3. And at every branching node, you have the relation that K1 would be equal to N1 minus N2 plus N3. Okay, so at every branching node, the frequency of the parent is equal to the frequency of the first child minus the frequency of the second child plus the frequency of the third child. Okay, so we call those when we, so these are ternary trees, of course. And when we assign frequencies to each node of this tree, we call it a decorated ternary tree. Okay, so this is a way, and this is a way to represent the iterates, and this is something that we have used since our first work with Tristan, Pierre, and Shalab. All right, so so as we said, U hat of the solution U hat at t at time k can be represented as a sum of decorated trees, and where the Fourier transform of the nth iterate is the sum of decorated trees that have scale n. The scale of a tree is the number of branching nodes. For example, this tree over here has 3 branching nodes. This is branching, this is branching, this is branching. So this is the scale of the tree. Okay, and as we said, we want our quantity of interest is the expected value of the mass density. So this is, sorry, oops, sorry. So the value of interest is the mass density. So we'll write this as the expected value of U hat of Tk, U hat of Tk bar. Each one of those, you express it as trees, and this you express it as a sum of trees. So when you take the expected value, you'll be taking expected value of the pairing of 2 trees. You'll take a tree that is coming from the expansion of U hat, and this is a tree that is coming from the expansion of U hat bar. Okay, so we call this pairing a couple when you have 2 trees that are paired to each other. And because of the Fourier modes that are paired according to Kirchhoff laws, the leaves of those trees, so these endpoint modes, have to be paired to each other. So here we denote this pairing in terms of the color of the node. So this node is paired with this node. And if it's paired with this node, then you have to assign them the same frequency. This node is paired with this node, etc. And as we said, whenever 2 leaves are paired, their decoration will have the exact same frequency. Okay, and this ultimately goes back to this Kirchhoff law that has to hold. All right, so this is this tells you how to express the expected value of U hat of Tk squared as a sum over couples of trees. We call them just couples. Okay, so there are 2 enemies to overcome. The first enemy is that there are order of n factorial couples at scale n. So you notice that if you're looking at couples that have scale n, those will have order of n leaves, and there are order n factorial ways to pair those leaves. Okay, to pick to partition them into sets, into 2-element subsets. Okay, there are n factorial ways to do that, and there are and as such there are order n factorial couples, and this we will see imposes a big problem for us. The second enemy, which is relates to the criticality of the problem that we mentioned before, is the fact that the n plus first iterate is only better by the nth iterate by a factor of delta, okay, rather than a factor of L to the minus epsilon for some epsilon, okay? And this is a reflection exactly of the critical nature of the problem that I will discuss next. Okay, so the kinetic time scale can be understood as the longest time scale for which the power series expansion, so of the solution U, this expansion over here, you can think of it as a power series expansion of U. It is the largest time scale for which this power series expansion is valid, okay? So in our previous work with the Udeng, we treated the full subcritical regime. We said that we were able to reach times that are order of L to the minus epsilon times the kinetic time scale. So in that case, each n plus first term is better than the, sorry, each n plus first iterate is better than the nth iterate by a full factor of L to the minus epsilon. As such, from a caricature point of view, this means that if you look at the nth iterate un, okay, then so the size of the nth iterate would be something like L to the minus epsilon, capital N, okay? And if you want this thing to be a small term, something like L to the minus nu, or less than L to the minus nu, all you need to do is expand up to n, that is order of epsilon inverse, okay? And this would be sufficient to prove an approximation result on this time interval, which is shorter than the kinetic time interval by a factor of L to the minus epsilon, okay? So, and as we said, this requires you to do an expansion of your solution up to a finite order, a large but finite order. And it's still highly non-trivial to do the estimates over there, but one can exploit the subtle combinatorial structure at the level of the trees in that case. So in our setting over here, we don't have this improvement or this level of gain from the n plus first iterate to the compared to the nth iterate. So in that case, as we said, we only have a delta gain, and as such, the size of this un could be at best order of delta to the n. Okay, and if you want to make this less than L to the minus nu, you need to let n to be at least as large as log L over log delta inverse. In other words, you need to let n diverge with capital L. Okay, in order to overcome this problem that criticality imposes. Okay, so let me talk a little bit about the second enemy that one has to overcome as well, which is the factorial divergence, which is arguably the most serious enemy one has to address. So as we expected, as we said, the expected value of un squared is the sum of an n factorial number of couples, can be represented as a sum of n factorial number of couples. And if each of those couples have size delta to the n, as we said before, we said we expect at best that those couples will have size delta to the n, then we are doomed in that case, because you'd get delta to, so you'd get delta to the n times n factorial, and this cannot converge. If you have as a toy example or calculative example, if you have a power series an t to the n, and if an is grown factorially, then the radius of convergence is 0. So the central question that one needs to answer, which turns out to be the right strategy to take, is the following. Can one classify the couples into groups such that those groups that saturate or almost saturate the worst case scenario estimate, which is delta to the n over here, okay, there are relatively few. For example, can you show that they are order of c to the n instead of n factorial? Okay, so exponential growth is allowed, but factorial growth is bad. Okay, so can we show that the worst case, the couples with worst estimates are few, they are maybe exponential in n, but all the remaining couples, which are factorially many, okay, have much better estimate than the worst case scenario. They satisfy much better estimate than this delta to the n. Okay, typically you'd want them to have a gain of powers of L which is sufficient to kill this factorial loss. Okay, and this turns out to be our strategy. And once you embark on this strategy, the first step is to identify those largest couples, or those couples that lead to the worst type of estimates. And the first hope is to show that those couples that lead to the worst kind of estimates are exactly the ones that converge to the wave kinetic equation. They are the leading couples that converge to the iterates of the wave kinetic equation. It turns out that, of course, those leading couples have those saturated estimates, but they're not the only ones that have saturated or almost saturated estimates. Turns out that there are 3 families of couples that have almost saturated couples that one can identify. The first family is what we call regular couples, and these are couples that contain inside them the leading ones that you like, and you want them to converge to the iterates of the wave kinetic equation, but they also contain many other couples that one has to show that they cancel out in the limit, and they do. The second family of couples that satisfies almost saturated estimates is what we call irregular chains. I won't be describing them here for the lack of time, but we'll probably discuss them when we go into the details of the work towards the end of the month. So these are called irregular chains, and they also feature almost saturated estimates, but they also feature a major cancellation that allows us to control them. The last family, or the last enemy here in terms of couples that satisfy almost saturated estimates, is what we call also type 2 molecular chains. Again, I'm sorry for this cryptic notation here. I won't be going into the details of describing what those mean. And those also can potentially satisfy almost saturated estimates, but they have better L1 in time bounds, which is what allows to accept their contribution. Okay, so once you identified those potentially most dangerous terms, the good news is that indeed there are only C to the n such couples. Okay, and whereas all the remaining couples do feature a gain in L. Okay, the factorially many remaining couples feature a gain in L, and this is the context of our main rigidity theorem, which is arguably the most important theorem of our work. Okay, so what does the theorem say? It says that if you perform a type of surgery on an arbitrary couple, and the purpose of this surgery would be to remove those 3 culprits that I discussed in the previous slide, to remove those regular subcouples, the irregular chains, and the type 2 molecular chains. So these are exactly the structures that lead to almost saturated estimates. Then in that case, you are left with a structure that has size R. And the important thing is that this structure, it features a gain of the form L to the minus R. So it features a gain L to a power that is comparable to the size of this structure. Okay, and this is really good. The reason why this is good is the following. This is enough to offset the factorial divergence because the number of such structures is R factorial. Okay, remember if we were looking at tree of size R, of size n, the number of couples associated with such trees is n factorial. So if we are dealing with a structure of size R, the number of such structures is R factorial. So but we have a gain of L to the minus R for such couples. So if we want L to the minus R times R factorial to be an error term, so to be something like L to the minus nu, it is enough to have that R is, say, less than log L. But this is the case because, as we said before, we will be expanding our solution up to order capital N, which can be taken to be essentially logarithmic in N. Okay, so this is enough to this choice is enough to both deal with the criticality problem and with the factorial divergence or the factorial explosion problem in that in our setting. The proof of this rigidity theorem is quite sophisticated, and the basic idea, or the most important idea, is to recast this problem of counting couples into counting another family of combinatorial structures that we call molecules. I'll show you a picture of such molecules on the next slide. And after you recast this in the language of molecules, the idea is to run something like a computer program to reduce these molecules effectively in order to be able to count them. Okay, so you put an algorithm, and this algorithm, by the end of it, we prove that our molecules have been accounted for. So this is a couple. This is the same couple that I drew a few slides ago. The problem with counting using couples is the following, is that the pairing structure that we talked about between the leaves is a highly non-local structure. You can have a leaf over here that is paired with a leaf that is very far away in the tree. So in order to do the combinatorics effectively, we need to replace that by something that encodes the same amount of information, but makes this pairing structure a local thing. And this is what a molecule looks like. Basically, so these are what we call the atoms of the molecules, and each atom of the molecule is identified with a branching node. So basically, an atom represents this branching or local family, if you like, over here. Okay, so for example, this corresponds to this branching node. Okay, and the fact that this thing, this branching node has this branching node as its parent corresponds to drawing an edge over here. Okay, so each thing over here is represented by, each one of those is represented by an atom, and the edges between the atom signify the pairings or the parent-child relationship between those branching nodes. Okay, and this makes this pairing structure a local structure, which allows us to reduce such molecules, which of course can be very large molecules, can we reduce them and count them in a more effective way. Final remarks is that the analysis of each of the couple families that I mentioned, that the regular couples, the irregular chains, the type 2 chains, each one requires a sometimes completely different genres of argument, which range from combinatorial constructions to analytic ones, and also number theoretic ones when we analyze the regular couples. And once this picture is made clear, once you understand the iterates pretty well and all the Feynman diagrams pretty well, the estimate on the remainder term becomes relatively easier and can be actually reduced essentially to the analysis above 5. This is something again that I don't think I have time to go into it. All right, so this is the end of my talk. Thank you for your attention.
Thanks, Zaher. Thanks for everyone. And do we have any questions among the audience?
I have a question. So going back to slide 17, where you talked about the different structures. So if you just go back a couple of slides.
Page 17, yes, 17. Okay, yeah.
So you mentioned you have these regular couples.
Yes.
Could you elaborate a little bit more? You say it's convergence to the iterates of the, is that the Duhamel expansion of the wave Kinetic equation?
Yeah. Okay, so okay. So if one looks at the iterates so there are a certain type of interactions or certain type of trees, actually certain type of couples are the ones that, these are the only ones that could converge to the iterates of the kinetic equation. Even if, for example, let me give the case of the first iterate of the wave kinetic equation. So in the first iterate of the kinetic equation, there are two types of couples that can give you the first iterate of the kinetic equation. There's the couple that looks like this, K1, K2, K3. And this is K, K1, K2, K3. So you have two trees of scale 1, and those trees of scale 1 are, you have this paired with this, you have this paired with this, and you have you have this paired with this. Okay, so this is one of them, and the other kind of couples that give you the iterates of the wave kinetic equation, or the first iterate of the wave kinetic equation, are this one. So this is, okay, so this is, you would have, this is K, K1, K2, K3. Okay, this would be the same as K2, this would be K3, and this would be K, and then this is paired with the trivial tree that is K. Okay, so again, if I want to draw them in terms of color, this is paired with this. This is paired with this, and finally this is paired with this. And of course, you can have this branching over here, and there are basically 3 other ones that look like this. Okay, plus their symmetries, which multiplies that by 2. Okay, but these are basically the building blocks of the regular couples. Okay, so these, if you can construct trees using only those structures. Basically, you pick this thing over here. I can do it actually using copy paste. Maybe it's a good idea. I can pick this over here and paste it right here. Okay, and I can keep doing that, right? And if over here in this case, I can I can replace, for example, the mode K3, and this which is paired with this, I can replace it by something like this and identify the 3 children. Okay, so this does not give you all the couples, of course. This gives you a very small family of couples, which are obtained by using those 2 building blocks. Okay, and this is what defines regular couples. So regular couples are ones that are built from those 2 building blocks. Okay, and there are C to the n of them. They're not factorial of them. There are only C to the n of them, of such regular couples.
My question is that if you sum all these couples, do you get the full kinetic wave equation? So in our first paper, we wrote down, we only did the first, like we only identified the first green ones that you did, and that's like the linearization of the wave kinetic equation at time 0. So right. If you kept all the couples and you sum them all together, does this correspond to the full Duhamel expansion of the wave kinetic equation, or is it just some subset?
No, so the full Duhamel expansion of the wave kinetic equation comes from as a subset of those regular couples.
Okay, so it's an even subset of the
regular. It's a proper subset of, so those regular couples, unfortunately, they don't give you only the iterates of the kinetic equation. So it's rather complicated. There's something we call dominant couples that are the ones that end up converging to the iterates of the wave kinetic equation. And then it turns out that one has to show that there are several beasts that come from the analysis of the regular couples, which by itself is around 50 pages. And those beasts go to 0. You need to show that they actually converge to 0 in the limit. And they do. Okay. Somehow it's in a very nice way, everything.
So the regular couples is a superset of the Duhamel expansion of the wave kinetic equation.
Absolutely. Yes, exactly.
But
and even that, it's still a C to the n of the number of those couples is C to the n.
Yeah.
But you still can separate these regular couple into 2 sets, one that are the iterates of the wave kinetic equations, and the remainder, which is small, that you can control, right?
Absolutely, exactly, yes.
Yes.
Exactly. I mean, the analysis of the regular couples is more or less sort of, like, as I said, each section has a different genre of analysis. The analysis of regular couples is more of a genre of analysis of explicit computations. Well, you really can do things explicitly by induction at the level of the regular couples.
Okay, good. I think Alex has a question. You want to ask it, Alex?
I think it's the same question as mine.
Oh, so I don't see. Okay, good. Okay.
So I've got a question.
Yes, sure.
Zaher.
Yes.
Is there an analog of the regular couples and the rest in the derivation of the Boltzmann equation of Gauss and Saint-Raymond?
In the derivation, well, I mean, I have to say that I'm not so familiar with that work, so okay. But I've heard talks. I believe there are in all those cases there's always the idea that of a separation of leading terms versus sub-leading terms is not uncommon. There's always the need to separate the leading terms and proving that the sub-leading terms are error terms, which is a common thing. I'm not sure how much the analogy can be pushed, but that's because I'm not very familiar with that work.
Okay.
Great.
Sorry, I have a question. So
Yes.
if you rescale the time appropriately, then you work on a small time interval of size delta, right? And
The kinetic side, yeah.
Yeah, and because of this, you get a small parameter in your system, and then you do what you do, so you make this expansion. So is this the only reason why you work on this small time interval, or there are some other reasons?
Yeah, basically, this is the ultimate reason. This will, because what we're doing is that we are matching the iterates of NLS with the iterates of the wave kinetic equation. And for that, you're using at the level of the wave kinetic equation something like Cauchy-Kovalevsky. So you need this delta to be small in order to guarantee that this is something that converges. And yeah, you need it all over that. This will be acting as your small parameter.
Okay. Thanks.
But also for delta not small, the wave kinetic equation might have bad solutions for if you wait for a long time. So you don't expect that this will lead anywhere. So it has to be small.
Yes, so you need some control on the wave kinetic equation. And as Jalal was saying, that for long times we're not sure that if the solution exists or not. So picking this delta small enough guarantees that the solution exists.
Okay, thanks.
Any other questions?
I have a question.
Yes, please.
So you assume that the initial datum, when you prepare it, is Schwartz class. Why do you need control on the derivatives for the initial data? Because the wave kinetic equation is well posed without any control on the derivatives. You just need decay, spatial decay.
Yes, but we need the derivatives in order to justify the approximation to the wave kinetic equation. One very simple thing to see why something like that might be needed is by looking, for example, at say you're looking at the iterates of NLS. The iterates of NLS are represented as basically sums over K1 minus K2 plus K3, something like n of, say, or square root of n of K1, but let's forget about the square roots, n of K2, n of K3. Whereas the iterates of the wave kinetic equation are represented by integrals over K1 minus K, or C1 minus C2 plus C3 equals to C. And this passage from the discrete to the continuous requires some level of smoothness on your n, right? So you can, in order to approximate a Riemann sum by an integral, you need some level of smoothness on your function. This is one place that this is used. Actually, we need the smoothness in several other cases, particularly to deal with irregular couples, irregular chains as well. But this is one reason why something like that is needed, particularly in the number theoretic part where you want to replace those sums, all the sums that appear in the couples by integrals, because as we know, the iterates of the wave kinetic equation are in terms of iterated integrals, whereas iterates of the NLS equation are iterated sums. So if you want to approximate those two things in the limit as L goes to infinity, you need some smoothness on your initial data.
So is it a technical assumption for now, or would you expect that the derivation could possibly hold without that kind of control?
I don't think it's a technical assumption, because it's something that you can even see the need for even at the level of the first iterate, okay, that converges to the first iterate of the wave kinetic equation. So the first iterate of NLS that would converge to the first iterate of the wave kinetic equation is something that looks, it's explicit, something that looks like sine t omega over omega squared, where omega is K1 squared minus k2 squared plus k3 squared minus k squared. Okay, and in the limit, you want to show that as L goes to infinity,
Okay.
this converges to n of k1, n of k2, n of k3, delta of omega equals omega. Sorry, I should use C1, C3, dxc1, dxc2, dxc3. And in general, if you take an arbitrary function without any level of smoothness, you cannot approximate a Riemann sum by an integral in general. Okay, so I feel that the requirement of smoothness of initial data, while it might not be needed to prove existence of the wave kinetic equation, it seems to be crucial. Some level of smoothness, I don't know what's the optimal one, but some level of smoothness seems to be crucial in order to justify the approximation.
Okay, thank you.
Okay, great. If there's no further question, we'll all thank Zaher again. Great talk, and we're looking forward to the technical details in a few weeks.
Thank you for listening.
Thanks, everyone, and we'll see you. Hope to see you next week. The talk will be by Sasha Korotevich, and he will talk. He did not give me the title yet, but it's about, again, wave turbulence and most likely water waves. So we'll hope to see you next week. All the best.
Ciao, ciao.
Bye.
Bye. Thank you.
Thanks, everyone. Bye. Bye.
Ciao to everybody.
Ciao, ciao.
Ciao, ciao.